All right, folks, this is our introduction to electrochemistry. Just a fun fact to start us off. This is from January 2017. You might remember this. And in fact, perhaps some of you had this device. The Samsung phones started to explode all over the place. They were making fire in people's pockets. There was a fire on a plane. And they came up with a new lithium battery with safety features that include a flame retardant chemical if it's damaged, if the battery is damaged at any time. So if the battery or the phone were to overheat or short circuit, this chemical would come out of a polymer-based separator in the battery, and it melts if the temperature of the battery goes too high and then releases the chemical. So they put that into place, and you know all about polymers now too. So some terminology for us. This type of chemistry is really different, but really important. If you think of any of the devices that you're using right now, they've got a battery power to them, and that's electrochemistry. So we're constantly, it's a huge branch of chemistry that's constantly evolving and trying to make batteries that last longer, that are more compact, etc. So some of the terminology that goes along with electrochemistry is this little saying that says Leo the lion goes grr. And Leo stands for loss of electrons oxidation, and grr stands for gain of electrons reduction. So anytime we have an electrochemical reaction going on, we have a loss of electrons happening and a gain of electrons happening simultaneously. So the loss of electrons, whatever element is doing that, we say that it's being oxidized, and the element that's gaining the electrons is being reduced. A little more terminology. Something that is oxidized is called a reducing agent because it's actually helping the other ingredient get reduced, and something that is reduced is called an oxidizing agent. So redox reactions, redox stands for reduction oxidation, so redox. They have, again, the two parts going on simultaneously, so both a loss of electrons and a gain of electrons. And the electrons gained has to equal the electrons lost. So law of conservation of energy, law of conservation of mass, all those things come into play here. A redox reaction can be split into two half reactions that show only the elements involved in the oxidation and reduction. And the other ones, we call those spectator ions. You've heard of spectators before. They're just sitting back and relaxing. They're not part of the action. So we're going to have a look at one of these types of reactions now. So this example has zinc plus hydrochloric acid. And this should be an arrow. As per usual, this program is great in lots of ways, but not awesome in others. It makes hydrogen gas and zinc chloride. So what we want to do is decide who is undergoing a change here. Now I have three different elements. I have zinc, I have hydrogen, I have chlorine. If I look from the left side of the arrow to the right side of the arrow, which elements do we think are undergoing some sort of change? One of them is a spectator. Let's see if we can figure out which one. So let's have a look at zinc first. Zinc is by itself on the left-hand side of the reaction, and zinc is partnered in an ionic compound on the right. So zinc is definitely undergoing a change here. The other ingredient that's undergoing a change is the hydrogen. Hydrogen is in a compound on the left, but hydrogen's by itself on the right. So let's have a look at what the two half reactions look like. Let's start with zinc. So zinc is in its solid phase by itself on the left of the reaction. On the right of the reaction, it's in its ion phase. It's in its 2+ form over here. However, we don't show that because, of course, we use the crossover with chlorine. But if I were just to isolate the zinc, it would be a zinc 2+ ion in that compound. Let's have a look at the hydrogen. On the left-hand side, there are two hydrogens because of that 2 out in front. And hydrogen, again, is in its ion form because it's in a crossover with chlorine, and hydrogen would have a 1+ charge. On the right-hand side, hydrogen's just by itself as hydrogen gas. And again, that's a Hofbrinkel, so it's an H2. So now what we want to do, is we want to decide who is the Leo, who's the grr, who's losing electrons, who's gaining electrons. So let's have a look at what is happening for zinc. Zinc has no charge on the left-hand side, but it's becoming a 2+ on the right-hand side. So if it's becoming more positive as it goes from left to right, it must have lost negatives. So I'm going to show those negatives as being lost on the right-hand side. So this is our Leo reaction, or oxidation, loss of electrons. So again, the zinc 2+ has 2 electrons that have come off. On the yellow side, the hydrogen side, we have 2H plus becoming H2. So it's positive becoming neutral. In order to neutralize the positive, we would have to add 2 electrons to get that job done. So this is my GR half reaction, my reduction. Down at the bottom, I've just made a little hint for you, and this is to help you when you're deciding where electrons should go. Both sides of a reaction must be balanced in terms of charge and number of atoms. So if we have a look at the blue reaction, the left-hand side is neutral, the right-hand side is 2 plus and 2 minus, which also makes a neutral. That means it's balanced in terms of charge. On the yellow reaction, again, I've got 2 negative electrons plus 2 positives to make a neutral on the left, and then on the right I also have a neutral. Balance doesn't mean neutral. This just happens to make neutral and neutral, but it just has to be the same on both sides. So let's say the left-hand side had a plus 2 charge, the right-hand side would also have to have a plus 2 charge. So let's try another one. We're going to try to complete the half reaction for the question below. We're going to label each half reaction as being an oxidation or a reduction, just like we did earlier. Again, I'm going to put that arrow in here for us, and we'll put proper subscripts in when we write it. So we've got zinc plus copper chloride making copper and zinc chloride. So again, looking at who's undergoing a change, starting with zinc, zinc is by itself on the left and it's in a compound on the right. So definitely undergoing a change. On the left-hand side, copper is in a compound on the left and by itself on the right. So again, it's undergoing a change. Chlorine is maintaining an ionic compound in both cases, so it's really not doing anything. So our zinc solid is becoming zinc 2 plus aqueous, and copper is in a 2 plus form in its ionic compound, and it's becoming a copper solid. So again, putting electrons in, starting with the blue reaction, we have neutral becoming positive. That means electrons must be lost, 2 electrons to create that 2 plus. There's my oxidation, my Leo. And again, my copper is going from 2 plus to neutral, so I'm going to have to add 2 negatives to neutralize it. So there's my GR half reaction. Let's go one step further and identify the oxidizing agent and the reducing agent. So remember that terminology here is opposites. So if this object was oxidized, it's losing electrons, it's the reducing agent. And our copper 2 plus was reduced, therefore it's the oxidizing agent. So that's how that terminology works. The last part we're going to look at is oxidation numbers, and these are arbitrary numbers that we assign to elements to help us count electrons in a reaction to determine whether an oxidation or reduction has occurred. I'm going to show you a table that gives you oxidation numbers, and from the ones that we know, we can use to find ones that we don't know. You have this table in your textbook. It's a little more complicated in your textbook, but you can use the one from your textbook. I don't know the page number offhand, but I'm sure you can find it. You're all capable adults. So on the left-hand side tells you the atom or the ion, and this certainly does not cover all the elements on the periodic table, but it covers the ones that are really commonly used, and we can use those to find the ones that are missing in a compound. So I'll show you how this works. So let's have a look at this part of the puzzle first, the atom or the ion. The first one is all atoms in their elemental form. If it's in its elemental form, it has an oxidation number of 0. So have a look at the examples, because that's something like sodium, that's in its elemental form, but also includes the Hofbrinkels. So that's a really key point, because Cl2, for instance, or O2, N2, for instance, those are all elemental because there's only one element. Those also would get a value of 0. The next one is hydrogen in most compounds. Hydrogen is almost always a +1 oxidation number. That's easy to remember because if we were doing ionic bonding, we would also give it a +1. Hydrogen in metal hydrides is a -1. So this is when a hydrogen is second partnered with a metal. This is really uncommon, so you're not really going to see that very often. You'll definitely see these ones a lot, but metal hydrides are pretty uncommon. The next one is O in most compounds are going to be a -2. And again, when we're doing crossover, that's what we would give it anyway, so this is going to be easy to remember. But again, there is exceptions. Peroxides, for instance, it's -1. H2O2 is a common peroxide, but peroxides aren't going to show up very often, so you don't have to look out for them too often. The next one is monatomic ions, mono meaning one type of element in the ion. And the oxidation number is just going to be the same as the charge of the ion. So again, if I have a sodium positive, it's a 1 plus charge. If I had an Mg2 plus, the oxidation number is +2. Notice a little bit here, we don't really get too fussy about whether the plus or minus is to the left or the right of a number, but this is actually the difference if you ever wanted to know. So Mg2 plus, 2 plus, the number and then the charge, that's how you write charges, and then the plus in front of the 2, that's how you write oxidation numbers. Not a big deal. I don't really care that much. Group 1 metals are going to be a +1. Again, when we're doing crossover rule, that's how we do them anyway, so that's pretty easy. And then group 2 are going to be 2 plus. Again, pretty easy because that's how we would do them for crossover anyways. So we're going to use those oxidation numbers to figure out oxidation numbers we don't know. So here are the rules. The first is that you're going to write the oxidation number above each element, there's one element, one oxidation number per element. And then the oxidation numbers must add up to the overall charge of the compound. So if the overall compound doesn't show any charges, then the oxidation numbers have to add to 0. And if there is a charge, like it's an ion, then the overall oxidation numbers have to equal that charge. So let's start with an easy one, CH4, and let's just write down our CH4 here, and we want to figure out what the C is in this compound. So again, we're just going to write oxidation numbers above each one, and the first thing we're going to do is we're going to go to the table and see if we can find an oxidation for the H. So if we have a look at the oxidation table, we have 2 values for H. H in most compounds is a +1, and then we also have H for metal hydrides. Ours is not a metal hydride. Carbon is not a metal, so our hydrogen is going to have a 1 plus oxidation number. I'm just going to write it above in red. Now I'm going to do a little bit of math, and a lot of this you can do in your head. Some of them are a little more complicated, but I'm going to show you the math this first time because we don't really know what we're doing yet. So carbon is an unknown oxidation number, so I'm going to give carbon an X right now. Plus, there are 4 hydrogens. Each one has a +1 oxidation number. Overall, remember the second rule for doing this is that the overall oxidations must equal the charge of the compound. Well, CH4 is neutral. Neutral is 0. So, solve for X. X is going to equal -4. So, we put a -4 up there, and this question is done. Next question, we want to know what's the oxidation number of all the elements in CO3 2-. Again, I'm going to write that out a little bit nicer for us. There we go. And our first job is to go to the table and see if we have oxidation numbers for C or O. So having a look, there's nothing for C, but there is for O. O in most compounds is a -2. The exception is peroxides. We do not have a peroxide, so we're going to use a -2. So again, our C is unknown, so we're going to do a little bit of math here. So we're going to use X for our unknown. Then we're going to add it to the oxidation numbers for oxygen. There are 3 oxygens, and its oxidation number is -2 for each one. And it has to equal the overall charge of the compound. In this case, it has to equal -2. So solve for X. So we get +4. Again, I'm going to put it up here for us. Our next example is a little bit tricky. This one is H2PO4-. So we have 3 elements this time. Again, job number 1, go to the table, see what's there. So as the last example, we have an H, so we have a +1 for H, and we have O's, which are -2. So we can use both of those in our question. Let's put them in. So we have a +1 here and a -2 over the O. So that means phosphorus is unknown, but that's okay. We'll set up a little equation here. So we have 2 of the hydrogens, they're +1 each, plus phosphorus, which we don't know, so that will be our X, plus 4 of the oxygens, they're worth -2 each, and the whole thing has to equal to a -1. So again, let's do the math, solve for X. So working out our X, we should get a +5, which we will write above the phosphorus. So the way we use them normally, we do that process, but we use it in a bigger context. So we go back to an equation like the one that I've got below here, and we can use it to figure out who's undergoing the oxidation and the reduction. So that's what we're going to do next. So we're going to take this formula, C2H4 plus O2 making CO2 plus H2O. It doesn't really matter about the balancing, so I'm just going to leave that out. But what we're going to do is we're going to put oxidation numbers above each element, and then we're going to use the oxidation numbers to see who has undergone a change in oxidation number. And that will help us figure out who lost electrons, who gained electrons. So again, using the table, the hydrogen is a +1. O2 is in its elemental form, so that one is a 0. CO2, the O2 is a -2. H is a +1. Oxygen is a -2. So those are the ones we know. Now we're going to work out the ones we don't know. So it's the same process as before. Starting with element number 1, we have 2 C's. So this one's a little bit different. We're actually going to have to do a 2x plus 4 of the +1s equals 0. Let's work out x. So here x is -2. We're going to write that above. So the first one is solved. Second one is solved. Let's go to the third one. So we have carbon, which is unknown, plus 2 oxygens at -2 each. They have to equal to 0. Solve for x. X is +4. And then our last one we have solved. So from here, now we want to see who has undergone a change in oxidation number. So looking from the left of the arrow to the right of the arrow, there are 3 different elements involved. Who lost electrons, who gained electrons? Let's have a look at carbon. Carbon is going from a -2 to a +4. So it has changed its oxidation number, so it is definitely participating in this redox equation. It's going from a -2 to a +4. It's getting positive. So it has lost electrons. This is my Leo half reaction. Having a look at hydrogen, hydrogen on the left is a +1, hydrogen on the right is a +1. So hydrogen is the spectator. Oxygen on the left is going from a 0 to a -2. It's doing the same thing on the right-hand side, but in 2 different places. So we just sort of circle everything. So it's going from a 0 to a -2. It's getting more negative, so it is gaining electrons. There is my reduction half reaction. So I can say that my carbon is being oxidized and my oxygen is being reduced. Right, so now it's time for you to try it on for size. Here are some questions to try. Yippee!